Hello and welcome. Today, we're going to pull back the curtain on one of the most powerful technologies out there, machine learning. We're going to break down exactly what it is, how it works, and maybe most importantly, why it's already changing, well, pretty much everything.
It's so easy to think of this stuff as some far-off science fiction concept. But the truth is, it's already here. It's deeply woven into the fabric of our daily lives, running quietly in the background. It's the invisible engine that powers everything from your Netflix recommendations to your email spam filter.
And just to give you a sense of the scale we're talking about, look at this. To make a Tesla drive itself, it isn't just one simple program. It's this incredible symphony of 48 different neural networks. Think of those as computer systems that are kind of modeled on the human brain. And get this, they were trained for 70,000 hours on some seriously powerful computers. And every single moment on the road, it's making 1,000 predictions. 1,000. That is the kind of power and complexity we're dealing with today.
But it's not just in fancy high-tech cars. Machine learning is completely revolutionizing industries you might not even think about, like agriculture. Systems like IBM's Watson are using these deep neural networks to help farming equipment learn the absolute best routes through a field, basically through trial and error. And they're using computer vision, which is literally giving computers the ability to see, to analyze the health of crops just from images. The result? Better food and way less waste.
And this is where it gets really important. It is literally saving lives. Just try to wrap your head around an algorithm that's been trained on over 2 million X-rays. It learns to spot tiny abnormalities with incredible accuracy, using a whole team of AI models that work together to find critical details in medical scans. Now, this isn't about replacing doctors, not at all. It's about giving them a kind of superpower, a new tool to catch diseases earlier than ever before.
Okay, so we've seen the what, and it's pretty mind-blowing. Now, let's get into the how. Here's our game plan. First, we're going to demystify the 3 main ways machines learn. Then, we'll zoom right in on the most common method, which is learning from labeled data. We'll even walk through a simple prediction task together. And finally, we'll pull back the curtain on the simple 3-step recipe that makes all of this possible.
All right, so you hear all these terms thrown around, right? AI, machine learning, deep learning, they're all connected for sure, but they are not the same thing. So let's start by clearing the air and demystifying some of these buzzwords.
This chart is a great way to picture it. Think of artificial intelligence as the big, overall goal of making machines smart. Now, within that giant world, you have machine learning, which is a specific approach that focuses on learning from data instead of being programmed with rules. And then, at the very core, you have deep learning. That's an even more specific technique within ML that uses those complex neural networks we talked about with the Tesla. So the first, and by far the most common flavor of machine learning, is called supervised learning. And the analogy here is perfect. It's exactly like studying for a test with flashcards. You give the machine a problem, that's the data, and you also give it the correct answer, that's the label. And after seeing thousands and thousands of these question and answer pairs, it starts to see the patterns, and eventually it can answer new questions all on its own.
Next up, we have unsupervised learning. Now, in this case, we don't give the machine any answers at all. We just hand it a giant, messy pile of data and say, go find something interesting. It's kind of like dumping a huge bin of Legos on the floor and having the machine automatically sort them into piles, by color, by size, by shape, all without ever being told what a red 2x4 brick is. It discovers the structure all by itself. And last but not least, there's reinforcement learning. This one is all about learning through trial and error. You have a little computer agent, and it takes actions in some kind of environment. If it does something good, something that gets it closer to its goal, it gets a reward, like a digital treat. If it does something bad, it gets a penalty. And over millions of tries, it figures out the best sequence of actions to get the most rewards. This is how AI learns to master incredibly complex games.
So those are the 3 big categories. For the rest of this explainer, we're really going to focus in on supervised learning, just because it's the foundation for so many things we use every single day. So the big question is, how does a machine actually learn from data that has all the answers? Okay, I know this looks a little academic, but stick with me, because it's actually really simple. Way back in 1998, a guy named Tom Mitchell came up with this classic definition. All it's really saying is that a machine learns if it gets better at some job as it gives it more experience or more data. And, this is key, we have to have a way to measure how much better it's getting. So more data should lead to a better score. That's it. So to learn, the machine needs data, and that data has a very specific structure. Let's look at this classic flower data set. The columns on the left, the measurements of the flower parts, those are called the features. These are the clues, the input you give the machine.
And that column all the way on the right, species, that's the target. That's the answer, the thing we want the machine to learn how to predict.
And this distinction right here is pretty much everything in machine learning. For supervised learning, you absolutely need labeled data. You need both the clues and the answer. You need that answer key. Unlabeled data, where you only have the clues, well, that's what you'd use for that unsupervised learning we mentioned earlier, where the machine has to find the patterns on its own.
Now, within supervised learning, there are really two main jobs we can ask a machine to do. The first is called classification. This is basically just sorting things into buckets or categories. Is this email spam or not spam? Does this patient have heart disease, yes or no? The second main job is regression. This is all about predicting a specific number. What's the temperature going to be tomorrow? Or how much will this house sell for?
Okay, enough with the theory, let's make this totally real. We're going to build a very, very simple model to do a classification task. We're going to try to predict whether a patient has heart disease based on some of their medical data.
So here it is. This is our training data. I know, it's super small, but it's perfect for our example. We have our 3 features, or clues, family history, blood pressure, and cholesterol, and then we have our target label, the thing we want to predict, heart disease, yes or no. The machine is going to learn from these 5 examples to try and make predictions on new patients it's never seen before.
Let's start with the absolute simplest model you can imagine. It's called a majority vote classifier. And this model is, well, it's not very bright. It completely ignores all the patient's data, the features. It just looks at our 5 examples, sees that yes shows up 3 times and no shows up twice, and says, okay, yes is more common, so I'm just going to predict yes for every single patient from now on. And how does it perform? It has an error rate of 33.3%. So it's wrong a third of the time. Not great, but it gives us a baseline. We know we have to do better than this. Okay, so let's try to get a little bit smarter. Our next model is called a decision stump. Instead of ignoring everything, it picks just one feature and makes a simple rule from it. For example, it might learn the rule, if the patient's family history is yes, then predict yes for heart disease. For everyone else, predict no.
So what was the result? Whoa! The error rate jumped to 66.7%. We made a smarter model, and it actually got worse. This is a super important lesson in machine learning. More complex does not always mean better. Sometimes a simple rule can just be plain wrong.
So we've seen a really simple model and one that's slightly more complex. But that begs the question, how does a machine actually find the best possible model out of all the trillions of options? Well, it all comes down to a simple 3-part recipe.
This is it. This is the secret sauce. All supervised learning at its heart follows this 3-step recipe. First, you define all the possible models or rules the machine is allowed to choose from. That's called the hypothesis space. Second, you give it a function to measure how wrong each of those models is. We call that risk or error. And finally, step 3, you unleash a search process called optimization to sift through all those possible models and find the one single model that has the lowest possible risk. Propose models, measure their error, and find the best one. That's the whole game.
And that brings us full circle. We've seen that learning is really just this simple recipe for finding patterns and minimizing mistakes. The examples we used were tiny, 5 patients, a handful of flowers. But what happens when you apply that exact same recipe, not to 5 data points, but to billions? What happens when the experience you give a machine is nearly the entire internet, the sum total of human knowledge, text, and images? That is the question that is defining our present, and it is absolutely going to shape our future.